Hello. Okay, hold on. Hello. This is very weird. Okay, so I'm just going to start going over a couple of the problems. I'm going to start with number 4 because Amy asked, and what Amy says I do. So number 4, I'm just going to check and make sure this is in the picture, so hold on, sorry. Technical difficulty. Okay. Okay, find the equation for the horizontal tangent line to the curve given in number 3. So I figure to find a horizontal tangent line, we want to know when is the derivative equal to 0. Okay? So I already took the derivative in the problem before. So if you had trouble with number 3, here's the derivative of that problem. So the derivative of number 3 would be, the derivative of 1 is 0, and then you would have root 2 times the negative cosecant of x, cotangent of x, plus the derivative of cotangent is negative cosecant squared x. So here's my derivative of the function that I'm talking about, and I just want to find out when is this equal to 0. I'm checking one more time to make sure this is in the screen, because no one else is in here to film it. Okay. So I'm trying to find out when is this equal to 0. So from here, it's like the algebra and the trig that's a mess. So what I did was I factored out a cosecant, a negative cosecant. So I took a negative cosecant x to the front. So then I have root 2 times cotangent x plus one of the cosecant x's left equals 0. Okay, I took out this cosecant and this cosecant. I took both of them as negative. So I have left root 2 times cotangent x plus just one of these cosecants left. So I kind of have two things. I have either the negative cosecant of x equals 0, or I have root 2 times the cotangent of x plus cosecant of x equals 0. If I deal with this one first, cosecant is negative 1 over sine x. Well, I can't have a fraction with a 1 on the top ever equal 0, because for a fraction to equal 0, the top has to be 0, so since that's never going to happen, I don't have to worry about that particular part of the solution because it's never going to happen. So I just have to look at this. So I expanded this to take a look. Now cotangent is cosine of x over the sine of x, and cosecant is 1 over the sine of x, and that equals 0. So, okay, I've got these two put together. This is really root 2 cosine plus 1 all over sine, since it has the same denominator. So for this to equal 0, I only have to worry about the top equaling 0. I don't have to worry about the bottom, because if the bottom were 0, it would make the function undefined. So I look at this, I go solve it. I have the cosine of x has to equal negative 1/2. I'm sorry, 1 over root 2. If I bring the 1 over and divide by root 2. So I'm figuring, let me move up here, and let me see if that's still on the screen. Sorry. Okay, move over a little bit. If I have the cosine of x is negative 1 over root 2, I need to remember that that's the same thing as negative root 2 over 2. If I rationalize this and multiply by root 2 over root 2, I would get this. So that's on the unit circle, that's easy. That happens whenever I am here or here. So that happens at 3 pi over 4 and 5 pi over 4, but the beginning of the problem said only to take into account when the x value is between 0 and pi. So the only x value I have to worry about is 3 pi over 4. So the question asks, find the equation for the horizontal tangent line when all of this stuff happens. Okay, so I know that the horizontal tangent line is happening when x equals 3 pi over 4. So I'm going to erase this for a second and have that. So I know I have a horizontal tangent line when x equals 3 pi over 4. Well, that's not the equation of the tangent line. That's just the x value in which it happens. So I know that the slope equals 0 for my horizontal tangent line. I know the x value is this. I got to go find out what the y value is when I have this x value. So I got to go take the original function, 1 plus root 2 times cosecant of x. And I have to plug in 3 pi over 4 for x, plus cotangent of x, and that's 3 pi over 4. Okay, so I do all this. I get 1 plus root 2. The cosecant of 3 pi over 4 is cosecant's 1 over sine. So the sine of 3 pi over 4 is negative root 2 over 2. Plus the cotangent of 3 pi over 4. Oh, I'm sorry, wait, this is positive. Sorry, 3 pi over 4 is on the top of the circle. That's positive. The cotangent of 3 pi over 4 is negative 1. So reducing this, the 1 and the minus 1 are going to become 0. This fraction within a fraction is going to flip and multiply. So I'd have root 2 times 2 over root 2. When I flip this and multiply, my root 2's cancel and I get 2. So the original question is find out the equation of the horizontal tangent line. So if the tangent line is horizontal when the derivative is 0, and the derivative is 0 when x equals 3 pi over 4, and y equals 2, well then, if I'm thinking about where that is, that point is at 3 pi over 2, 2. Say it's here or whatever. And it's a horizontal tangent line. Oops. Going through that point. So what's the equation of it? Y equals 2. Final answer, y equals 2. That's the equation of the horizontal tangent line. It's tangent to the curve they give us at that point that we found where the tangent's horizontal. Okay. Okay, so let's do a couple more. I'm trying to go through some of the ones that I know are pretty tricky. I think you guys, I heard people getting number 2. Number 5, I'll go over in person. Number 7, do what we did in class a couple weeks ago. Make sure it's continuous by plugging in 0 for the x's and setting the two parts equal. And then make sure it's differentiable by taking the derivative of both and plugging in 0 for the x's and making sure that works. So what I mean by that is, for number 7, to make sure it's continuous, we're going to plug in 0 for x for both parts. So I'm going to get 0 plus b has to equal the cosine of 0. So the cosine of 0 is 1, so b has to equal 1. So I know that's the case. To make it differentiable, I've got to go take the derivative of both pieces. The derivative of x plus b is going to be 1, because the derivative of x is 1 and the derivative of b is 0, because b is a constant. And the derivative of cosine is negative sine. So for it to be differentiable, I need these two to also match when x is 0. Well, x is never going to be 0 here, it's just 1. So 1 is going to have to equal the negative sine of 0. Well, that's a problem, because the negative sine of 0 is 0, so this is 0. 1 does not equal 0, so it's not differentiable. So there is no value that's going to make it work, because it's just not differentiable no matter what value for b you pick. So you can pick a value for b to make it continuous. You cannot pick a value for b to make it differentiable. All right, number 8, to find the 999th derivative. I won't tell you the answer yet, but just go through and take your original function to be cosine, take the first derivative, the second, the third, the fourth, and you're going to see a pattern that starts to happen. So how many times will that pattern happen by the time you get to 999? That would be the trick for that one. For 9, I'll go through the answer. To take the derivative of that, it's a product. I'm sorry, it's a quotient, so I need quotient rule. So I would have the bottom times the derivative of the top, and the derivative of the top would be u prime minus 2v prime. Be careful, these are functions, so when you take the derivative, I have to list it as u prime. We did a problem like that before. So bottom derivative of top minus the top times the derivative of the bottom all over the bottom squared. Plug in the values for u and v prime, and I got negative 4 as my final answer. So go and check that and see what you get. Number 10, we'll go over this in class, but I guess I'll just tell you that it's A is false, B is false, C, D, and E are all true. So we can go through that together. Number 11, the difference between average rate of change and instantaneous rate of change. So if I want to find the average rate of change of sine of x over the interval 0 to pi over 6, I want to find f of pi over 6 minus f of 0 over pi over 6 minus 0. So I'm just finding the slope. Okay, when I do that, when I plug it all in, I'm going to tell you I get 3 over pi. So see what you get, see that you can get 3 over pi. The instantaneous rate of change is the derivative. So the derivative of sine is cosine. And they're asking me to look at f prime of 0 and f prime of pi over 6. So in other words, here's what the average rate of change is from 0 to pi over 6. It's 3 over pi. That's approximately, say, like 1 point something. Oh, no. Yeah. No, actually it's not. It's a little bit less than 1. So it's a little bit less than 1. This, when I take the derivative, it's cosine. When I plug in 0, I get 1. When I plug in pi over 6, the cosine of pi over 6 is root 3 over 2. So I get something, when I take the instantaneous rate of change, I get something between 1 and root 3 over 2. I'm sorry, when I take instantaneous at 0, I get 1. Instantaneous at pi over 6, I get root 3 over 2. The average rate of change is about 1. So, I don't know, you're just kind of looking at the difference there, that I can tell you exactly how fast something was changing if I use the derivative. I can only give an average when I use the slope formula. Big hairy deal, that's not that important. Okay, 12 is an awesome problem. So here's some hints to start it, and I'm sure we'll end up going over this one in class together. Number 12. The idea here is that if I have a parabola and it's tangent to a line, a couple things are happening. Number 1, they tell you, okay, this is the parabola. First, they tell you the parabola is going through the point 0, 1. So the first thing I know is, well, if this parabola is going through the point 0, 1, then I know I can plug in 0, 1 and it's going to be a solution in this parabola. The second thing I know is that if this parabola is tangent to the line y equals x minus 1, then I also know that this parabola and this line share a point. Right? Because if they're tangent to each other, then they are going to meet at one point, and the parabola is going to do its thing, and the tangent line is going to go off from it. But at one point, they're going to meet. So I know that this parabola and this tangent line must have one shared point. So I do know that ax squared plus bx plus c is going to equal x minus 1 at least one point. And the point I'm talking about is where the tangent line is. It's possible they cross somewhere else, but if we get 2 answers, then we'll know when that happens. So the first thing we know is the point 0, 1 is a solution here. So I can plug that in for the y and the x. So I know that when y is 1, x is 0. So 0 and 0 and c. So now I know that c is 1. The second thing is, if this parabola has this tangent line, then they must share a point. So the parabola and the tangent line must be equal at some spot, and I'll be able to get some solution from that. So I will plug in 1 for c, and that'll give me ax squared plus bx plus 1 equals x minus 1. Oh, I wasn't thinking about that. Sorry. Downtime. You know what? This isn't as helpful as I thought, because I forgot, I didn't read further. What I also know is that it says these two are tangent to each other at the point 1, 0. So I don't even have to do this, actually. Sorry. This point is also going to be a solution for this parabola, because that's the spot where they're tangent. So I also know that if I plug in 0 for y, I should get 1 for x. So a plus b plus c, and I know that c is 1. So I know that a plus b equals negative 1. Get it? Sorry. I forgot that they give me another point. They tell me where this parabola is tangent to this line. So I was trying to solve this. I wouldn't have got, well, I guess maybe if I had solved this, I could have gotten this point, but they're telling me where it is, so I might as well use it. I might as well plug that point into that parabola and get that a plus b is negative 1. Okay, so I know what c is, I know what a plus b is. Once I get like a plus b equals something, that should tell me I'm looking for a second equation. So what I also want to know is, since this is tangent to this at that point, I know what the slope of this should be at this point. I know that y prime should equal 1. Because the slope of the tangent line is 1, I know that that's what the derivative of this should be. So if I take the derivative of that, which is going to be 2ax plus b, I know that it should equal 1. And I know that it should equal 1 when I'm at the point 1, 0. So if I plug in 1 for x, I'll have 2a plus b equals 1. I know that that's also going to be true. This is a hard problem, right? So this piece of information is this parabola is tangent to this line, so therefore this parabola must have a slope of 1 at that point 1, 0. So I take the derivative of this parabola, it must have a slope of 1 when x equals 1. So when I plug in 1 for x, I have this. Now I solve these simultaneously, do substitution or whatever, and I get a is 2 and b is negative 3. So I know we might have to go over that together, but there's your basic overview of this problem. It's tricky. I would expect something like this on the test. So a couple things, I'll just say it again. Number 1, this parabola I know goes through this point because they tell me. So plug this point into here. This parabola also goes through this point because that's where it's tangent to this. So I can plug this point into it and get this information. And since this parabola is tangent to this line, this parabola has the same slope as the line at that point. So the derivative of this must equal 1 at that point, and it gives me another equation, and I can solve for a and b. Okay. Happy Yom Kippur, everybody. 14 and 15, I think you can do from what we went over before we got to the trig stuff. Make it continuous, make it differentiable, solve both things together. For number 14, a is 1/3 and b is negative 4/3. And for 15, a is 0 and b is 1. I do know that I skipped 13. You should go back and look at your pre-cal notes and see what you think about that. If you remember, how do you graph the absolute value of sine, and how do you graph the absolute value, or sine of the absolute value of x? When you graph the absolute value of sine, that means that everything up below the x-axis should now be above. So number 13, the sine of x, all absolute valued. This means that sine usually goes like this, but instead all of these downward humps should be up here. So if this is what it looks like, where is it not differentiable? And for the sine of the absolute value of x, that means that everything on the right should be mirrored on the left. So every x value or negative x value will give you the same thing. So everything I have on the right should just be mirrored on the left. Whoops, not like that. Should be mirrored on the left. So it'll look something like that. So where is this not differentiable? We'll go over that on Thursday. Number 16. I would rewrite 16 as a piecewise function. Remember how to do that? We go, follow the same rules as before. Look at the absolute value, see what makes it 0. Set up a little number line, and since 0 makes that 0, plug in numbers bigger than and less than. So if I plug in like 1, I get a positive value in here. So I just drop the bars and make it parentheses, and I would get x times x, which is x squared. Plug in a number less than 0, like negative 1, and I get a negative number in here. So drop the absolute value bars, but make it negative. So it would give me negative x squared. So the function itself is going to look like negative x squared when x is less than 0, and x squared when x is bigger than 0, and I can make one of them equal to. The question is, does the second derivative exist? Well, if I take the first derivative, I'm going to get negative 2x when x is less than 0, and then I'm going to get 2x when x is greater than 0, or equal to. I can actually answer this question here, but let me just keep going. Let's look at that second derivative. I'm going to get negative 2 when x is less than 0, and I'm going to get 2 when x is bigger than 0. Actually, well, I'm not sure if I keep that equal to, but it doesn't matter. So, is it differentiable for the second derivative? Well, look at it. The second derivative looks like this. It's got a line at 2 this way, and then a line at negative 2 this way. There's no way that's differentiable. First of all, this isn't the function. This is the derivative. But it's not differentiable here because I know that they don't match. I know my y values don't match up at 0, so it's not differentiable. It's probably not a good idea to look at that graph because you might get confused. So the second derivative doesn't work because at 0, I don't have my derivatives matching up. I also could have known from what came before it that this graph looks like this. When x is bigger than 0, it's like this. When x is less than 0, it's like this. Well, since there's a corner here, the derivative is not going to work. So if I just looked at this and I see I have a corner, well then this is not differentiable, so I can't take a second derivative anyway. Or just take all the derivatives, look at the second one, and be like, oh, nope, they don't exist, or they're not the same when x is 0. All right. Number 17. Good question. Number 17. For the following, find k such that the line y equals x plus 4 is tangent to y equals k root x. This is kind of what I was talking about before. Two big things are true about this. First of all, we know that they have the same slope, where we're looking at, and second of all, we know that they share a point. Okay? Because if these are my two curves, they're going to share a point wherever they meet, wherever they're tangent. They're also going to have that same slope wherever they're tangent. So the first thing I could look at is their derivatives. So the derivative of this is 1, and the derivative of this is going to be k over 2 root x. So since I know they have the same slope, I know that their derivatives are equal. So I know that the slope of this has to equal the slope of this. And I also know that they're equal to each other at some point, so I know that they share a point. So I know that x plus 4 also has to equal k root x at some point. Well, since I have two variables here and two variables here, I can solve these simultaneously. It's up to you how you want to do it. Maybe you want to substitute or solve for x and plug that into this, or solve for k, and whatever you want to do is fine. I got to the point where k equals 4. So see if you can get that, and then we can go over it. So there you go. I hope it was fun. I hope you had a good time. I hope that somebody found me along the street and helped me to the gas station, or I made it to the gas station. So that's it. I hope you're having a good day. See you on Thursday.